the force trying to hold the valve open, Fo equals PC casing pressure AB below pressure minus AP port pressure plus PC casing pressure AP. Okay, and therefore PC AB minus small b I have written AP plus PCAP equals PDAP AB. Here PVC equals PC, PVC equals PC. So if PVC is a pressure in the casing at which the valve will close under opening condition, at which the valve will close under operating condition, Okay. So PVC AB minus AP, so plus PVC AP equals PDAB. PD means dome pressure, or PVC equals PD. Okay. So you have to remember this formula, this relationship, how you are deriving. So in exam I can twist a little bit and I can give the question. If you do not practice, so during exam you will get confused. And spread, another term is there. The spread is the difference between opening and closing pressure. So del P, spread is del P equals PD minus PT R 1 minus R minus PVC closing pressure. So P here PVC equals PD. Now del P equals PD minus PT R 1 minus R minus 1 minus R PD 1 minus R. So this implies R 1 minus R PD minus PT. So this is actually TEF PD minus PT. Okay, so you know TEF equals TEF. In a previous lecture you can see TEF equals 1 R by 1 minus R. This relationship is there in the previous lecture. So now using this one we can solve problem. Like if we give certain parameter, then you can find other parameters based on this formula. So this problem we solved in the last lecture actually. A pressure valve is located at 6,000 feet depth. Okay, so this is casing, this is tubing. I can assume there is one packer. Okay, one valve is here. So this depth is 6,000 feet. Not 6,000, 6,000 feet. Pressure in the dome. So your valve, if I enlarge this one, it will have one dome, right? So dome pressure is given 700 psi, and the tubing pressure 500 psi. PT is given 500. Okay, PT at the injection location actually. So because it is given 600 feet, so it is at injection location. Find the casing pressure at 6,000 feet required to open the valve. So you have to find PC. Okay, so that one solved already. Now in present problem you have to calculate del P. Okay, so to calculate del P, actually you have to use the formula del P equals, this is del P, right? Okay, so del P equals TEF and PD dome pressure minus PT. Okay, it is giving 22 psi. So opening pressure P VO equals P plus del P. Okay, so 700 plus 22, so 722 psi. psi. So maximum spread can be PT equals 0 will give del P maximum. Okay, and minimum when PT equals PD dome pressure will give del P minimum. Okay, so when tubing pressure is becoming exactly as dome pressure, so it will give del P minimum, and PT 0, that time del P will be maximum. Balanced pressure valve. So I said like there are two type valve actually, unbalanced and balanced pressure valve. In unbalanced pressure valve, tubing pressure also will be affecting your opening and closing of the valve. But when you are talking about balanced pressure, only casing pressure will be controlling the valve. Okay. So in balanced pressure, no dependent on tubing pressure, closing and opening at the same pressure, that is dome pressure. Okay, dome means this nitrogen dome here, dome pressure is here. Okay, the same pressure will be used. Spread is 0 regardless of port size, because PT is not affecting, so spread or del P equals 0 all time. Now a problem: if a dome pressure is 700 psi, opening and closing occurs at 700 psi. Now if I give any tubing pressure, your answer will be same actually, because it is not affecting tubing, it is not affected by tubing pressure. If tubing pressure is 400 or 300, it does not matter, it does not affect the opening or closing the valve. Okay, so in exam I can give, like if dome pressure is 1000 and tubing pressure let's say 500, so what will be the opening and closing pressure? So it is not affected by tubing pressure. Okay, or if I say its tubing pressure changing 400 to 500, what will be the opening and closing valve, whether it will be getting more affected by tubing pressure, because I am changing the tubing pressure, so it is not affected. Okay. Okay. So evaluation of gas lift potential, and this is taken from Kermit Brown book. Okay, so basically there are two types of gas lift system, you know, the continuous gas lift system and intermittent gas lift system. Continuous gas lift system, normally it will have very low port diameter and gas injection rate will be lower. In intermittent gas lift system, your gas lift port diameter will be larger and the gas amount will be injected, a very large amount of gas will be injected, because after certain time you have to inject gas, stop it for certain time, again inject. So you need very larger port area and higher amount of gas in one go. But in continuous gas lift system, your port area will be small. Port means the gas lift valve port area, and you are injecting small amount of gas and you are creating bubble. So it is bubbly flow. So purpose of gas lift valve basically to unload the fluid from the wellbore and to control the flow. Okay. Location of valve in the flow configuration influenced by available gas pressure for unloading, how much gas pressure is available. So that will affect fluid weight or gradient in the wellbore. So if it is purely water, like salty water or liquid, or if you have some gas amount, so that will also be affecting the system. Wellbore inflow performance relationship, so that will also affect your system. Wellhead pressure, if higher pressure is required, then your flowing pressure will be affected. So flowing pressure is affected means your drawdown is also affected. Casing fluid load, bottom hole pressure and well production characteristics. Okay, all these things will be affecting. Valve location should be known so that the dome pressure can be set at the factory. So at the initial, before setting up your gas lift valve, actually you have to know where you are putting your gas lift valve and what will be the fluid density and wellbore, all the characteristics, so that your dome pressure can be selected. especially if you are selecting your balanced pressure valve. In that case, it is completely controlled by dome pressure only. So, here how this gas lift system or any artificial system lift system actually affected, or artificial lift, how can it affect your production rate. So, if you can remember this productivity index IP or Vogel's curves of inflow performance relationship, you can see here liquid flow rate in Q axis and Y axis shows flowing pressure. Now, if you have zero flowing pressure, let's I have wellbore, okay, and this is my production area, perforations are there, okay, fluid is coming, reservoir pressure is here, PWF, flowing pressure is here, okay, and the difference, the pressure between reservoir pressure and flowing pressure is called drawdown, okay. So, if the drawdown is higher, then higher amount of fluid will be entering. Now, if I make flowing pressure 0, that means I am making big drawdown. Big drawdown means my flow rate will be very high. So, you can see in IPR curve, I can get absolute open flow and I get very high amount of flow rate. But my PWF or flowing pressure is becoming almost equal to PR. So, drawdown is almost 0. In that case, you can get very low flow rate, okay. Now, artificial lift can increase the drawdown. How? Let us say you have wellbore, okay, and you have PWF and PR here, okay, you have drawdown. Now, this column is fully loaded with liquid, okay. Now, what artificial lift will do? Artificial lift will remove the liquid from the wellbore, okay. So, if you have one, let us say one ESP is here, okay. What ESP will do is ESP will be removing liquid from the wellbore. When removing liquid, actually PWF is getting lower pressure from hydrostatic pressure, the hydrostatic load, okay. When it is getting lower pressure, your drawdown increase means more fluid will be entering into wellbore, okay. So, you see the picture A here, outflow performance is this one, this red color line, okay. It is not touching your inflow performance curve, okay. Now, you use one artificial lift and you get one curve like this. What will happen? If you get one curve like this, that means this outflow performance relationship OPR is touching your IPR. So, your production will be here, your flow rate, okay. This will be your flow rate, and in this case you reduced your PWF, okay. Let us say this is PWF 1, initially it was PWF 2, okay, or say PWF 0. So, initially it was PWF 0, then because of artificial lift you will remove some liquid. So, what happened? Remove some liquid, so hydrostatic column weight reduced and your PWF got reduced. When PWF reduced, the distance, the difference between PR and PWF increased. When both increased, more fluid will be entering into wellbore. So, you will get more production rate or more flow rate. So, the right side picture you can see, initially gas liquid ratio at 1, it was not crossing your IPR curve. Then you put certain artificial lifting system, your flow rate become here, your PWF become here. Again you put some more efficient artificial lifting system, then your flow rate become higher, okay. So, Q1 maybe, Q2 maybe, this one PWF1 maybe, PWF2 maybe, okay. So, gradually you can see PWF flowing pressure is going down and your flow rate is increasing, okay. So, you are getting more productivity. So, in that way, now if you have any gas lift system, in gas lift system actually you are trying to change this PWF. When you are changing PWF, so drawdown is increased, drawdown increase means more fluid will be entering into wellbore and you will get more production. So, here in one book, artificial lift method by Nue, Springer book, so they have explained nicely using IPR relationship and your gas injection rate. Here you can see vertical axis depth, okay, this is depth, okay, this one pressure on the surface, okay, surface pressure means wellhead pressure, and this is casing pressure. Wellhead pressure means if wellhead requires 100 bar pressure, so that will be required as wellhead pressure, and SO means that is operating pressure, surface operating pressure they are saying. And bottom side, if you see wellbore here, okay, so initially let's assume your PWF is here, PR is here, so you have certain amount of small amount of drawdown, and because of that you are getting production, okay, but that is not sufficient to lift the fluid up to the surface. So this is gradient, okay. So inside fluid wellbore if you have, and if you see P1, this is P2, this is P3, this is P4. If I draw this one P1, P2, P3, P1, P2, P3, P4, the pressure, and this is the distance, distance maybe P1, this one D1, this one D2. So D1 pressure is high, D2 pressure is lower, lower like this. So I can get one line like this, okay. P1 means H rho G. So H is changing from the surface, that means my pressure also changing. So pressure also changing, H1, this is H2 rho G. I am assuming this rho is not changing, G anyway we are not changing. So the curve will be like this, okay, hydraulic gradient inside tubing. So here in green, the blue line is showing like this, okay. So and you can see this blue line is not touching the top portion of this y axis, okay. That means the reservoir pressure is not able to push the fluid up to the surface, okay. So liquid level will be up to certain level, okay, although wellhead is here, but liquid level is not reaching up to the wellhead, okay, because the pressure is not sufficient, reservoir pressure is not sufficient. Then what you do, you try to inject gas. When you try, okay, for that case, let's draw the IPR curve. IPR curve means like flowing pressure is here, and just opposite way I have drawn, like IPR curve will be like this, PWF by Q. Just put it in reverse order, and you make like this, PWF and Q, okay. So then IPR curve, this will become like this, okay. The same thing is drawn here at the bottom left corner. So curve is like this, okay. Now you are getting very high bottom liquid rate, okay. They have changed like this, this one Q, the one PWF, okay, they have changed like this. Now PWF is very high, okay, so you are getting, so PWF is very high, so you are getting more production, okay. You are not getting any production, so you have to reduce PWF so that you will get more production or more flow rate. So you inject gas, okay, so inject gas, so you change PWF. When PWF is changing, so you can see your flow rate is also changed, okay, flow rate also changed, and your PWF is here because of gas injection. So point of balance one term is there, point of injection term is there. Point of balance is that, like from surface, this is PSO, shows this vertical line, almost vertical line. PSO is actually casing pressure, okay. When you inject gas, okay, I have to draw one more picture, okay, this is your annular area, this is your valve area, okay, this is your valve, maybe this is one valve area. From surface you are injecting fluid, injecting. From the surface you are injecting. When you injecting gas, at this moment you will, your gas will just try to enter, okay, but you need some extra pressure, okay, some extra pressure from the surface, then your valve will be opening and you can get production, okay. So your point of balance will be like where liquid and gas will be balancing, but no production is happening. Then you increase further more pressure, then your production rate will start. So, point of injection will be here, okay, or point of balance will be here, okay, this is a point of balance, and but your point of injection okay. So, here also you can see point of balance, point of injection is here. So, from point of injection again you draw one curve, okay, draw one curve means there you got multi-phase flow, lots of gas injected. So, your hydraulic, that gradient will change, okay. So, now PWF, my figure you can see here, PWF was here, now PWF become here, okay, and you are injecting here somewhere, then the gradient, you are reaching the same point, but you got lower gradient, okay, because you got multi-phase flow, you are getting more production, but gradient changed. So, you are getting more production, okay. PWF change means your drawdown change means more fluid will be coming into wellbore, but your hydrostatic pressure from the top to the point of injection reduced. So, you are getting more production, PWF also changed.